will proceed in various coordinate system, multiple coordinate system, different coordinate system, and we'll see the water tank we are talking for a few sessions. The surface area of water tank, that is semi hemisphere. So that will proceed in a kind of a spherical coordinate system. So that is the idea. Calculating the surface area of hemisphere, semi-hemisphere water tank. So this is what we are talking. So calculating the semi surface area of water tank. So what we have done till now, if I have a hemisphere means if there is a xy plane, if there is a xy plane and there is a sphere. Okay, so if I have hemisphere, I think we have seen it. So if there is a hemisphere, okay, so this is better a sphere. So if there is a sphere and if I cut this sphere half, okay, if I cut this sphere half, then this portion becomes hemisphere. Now this is this is hemisphere. If this is hemisphere, this hemisphere, and then top portion, if I cut little bit, then this is semi hemisphere. The height is h. Height is h from the xy plane of the hemisphere. Below xy plane, lower hemisphere, I throw it away. So only top hemisphere, and in top hemisphere, the top is the top point. The radius of hemisphere is A. The radius of hemisphere is A. A is radius of sphere. So A is radius of hemisphere also. So if I have xy plane, from xy plane if I go top, then till top to xy plane, it is A. But we have cut from the top also little bit, so height is h. If height is h and radius is a, then what is the kind of the curved surface area? That is in discussion. And then we will see if top portion of the, this is a water tank. So top portion is covered and then bottom portion is covered and it is kept somewhere at height. Okay, it's very big. I told it is like 20-30 meter high. So it is like a railway department uh, water tank. So so it's like railway department water tank. It's very big. So if someone from here, he has to go here, then he has to take the stair. Through stair or ladder, whatever, he has to go there. It is that high, kind of a two-story building or something like that. It is that big. Now, if someone was to make this water tank with steel, okay, then bottom portion should be covered, then curved portion should be covered, and top portion should be covered. How much steel is required? So top portion easy to get, pi r square, bottom portion easy to get, pi r square, but the curved portion is difficult to get the surface. What we have done till now, what we have done is we started we started from the, what we have done till now is we started, okay, we started it from the kind of Cartesian coordinate system. So Cartesian coordinate system, if you try to find the surface area, then you have to find the position vector. Surface area, this is what we have seen. So if I have a sphere, and a sphere, consider that a sphere is centered at the origin. Sphere is centered at the origin. And then there is a point P. Origin to P, I draw a radial vector, position vector P. that is xi plus yj plus zk. If that is true, then z is nothing but, if this is xy plane, the height or function over x and y, z equal to fxy. If z equal to fxy, function over x and y, then what is z? X square plus y square plus z square equal to a square, that is the sphere algebraic equation. So z or fxy equal to square root of a square minus x square minus y square. So position vector p is nothing but xi plus yj plus zk, or square root of a square minus x square minus y square k. Now, if I find velocity vector, if I find velocity vector along x-axis, velocity vector along y-axis, and if I do cross product of two velocity vector, it gives me area. Area velocity vector. If I have area velocity vector, and if I calculate the magnitude, because area will be again a vector. So if I calculate the magnitude, it comes to algebraic equation. Now, area velocity vector's magnitude, that is algebraic equation, if I do integration, then it gives me area. If I have rate of collection, if I do integration, it gives me collection. If I have kilometer per hour, if I do integration with respect to the independent component hour, it gives me kilometer. If I have a velocity area vector, and if I integrate, it gives me the area. So that is the concept, and we did it. So now it came as, if it is dp by dx, if p is like that, then dp by dx is I plus dz by dx k. dp by dy, velocity vector partial derivative along y-axis, is j plus dz by dy k. If I do cross product, it becomes minus dz by dxi minus dz by dyj plus k. If I get the magnitude, then dz by dx whole square plus dz by dy whole square plus 1 whole square. Or we can say, if fxy is a function, then dfxy by dx is fx. F, and in the subscript, in the bottom, we write x, fx. That means dfxy by dx. If that is the case, then fx whole square plus fy whole square plus 1 square root is the algebraic equation. Now this equation, and then I have to integrate along the xy plane. That's it. That is the area. Now today the idea is that we will do everything in spherical coordinate system. So in a spherical coordinate system, fx means dfxy by dx. So here the independent component, if I see the xy plane changes into r theta plane in a spherical coordinate system. If it is r theta plane, then the vertical is fr theta, function over r theta. There it was function over x and y. Here function over r theta. If it is function over r theta, then what is f r theta? Whatever it is. If it is f r theta, then first is fx square plus fy square plus 1. Here it will be f r square plus f theta square plus 1, where fr is nothing but d of fr theta by dr. F theta equal to d fr theta by d theta, partial derivative along r, partial derivative along theta. Now what is fr theta? There fxy was a square minus x square minus y square square root. Here what is fr theta? Now if I have a hemisphere, if I cut the hemisphere and then I cut little top also, then I have semi hemisphere. The height is h. The bottom radius is a, that is the radius of the sphere. Top radius is r, any r. R is variable. If I keep changing height, r is variable. If height is 0, then r is equal to the radius of the sphere. If height is h is a, then r is 0. Okay, I would repeat it, reiterate it. Okay, so if I have a hemisphere, this is r theta plane, and half of the sphere I have here. Bottom half the sphere I kicked it. kicked out. Only half of the sphere is there. So at the r theta plane, the radius of the radius r theta plane is a circle. R theta plane is a circle. If r theta plane is a circle, the radius a is nothing but the radius of the sphere. Okay, the height at from the center, if this hemisphere is centered at the origin, then height at the center is a. Here the circular region radius is a, then height is also a, because a is the radius of the sphere. But at the height h it is cut. At height h it is cut. Height h where it is cut, there also it is a circular region. So at the base, at the r theta plane, there is a circular region of radius a. Then at height h, when I cut, there is a circular region of radius r, small r. So h r, and if I take diagonal, again it is a, because that is the radius of the sphere. So the height is nothing but a square minus r square, that is fr theta. Fr theta is the height. Then fr theta equal to a square minus h square, a square minus r square root. Now I have fr. Now I have dfr theta by dr whole square plus dfr theta by d theta whole square plus 1 whole square root. That is the velocity area magnitude. This magnitude I have to integrate along the r theta plane to get the surface area. That is the concept. Now if I substitute dfr theta by dr, then dfr theta is square root of a square minus r square. So dr will be minus r square root of a, I'm sorry, minus r divided by square root of a square minus r square. Square root of a square minus r square derivative with r will be minus r divided by square root of a square minus r square. Okay, and then dfr theta by d theta, d of square root of a square minus r square by d theta is nothing but 0, because there is no theta there, plus 1. So minus r, okay, minus r divided by square root of a square minus r square plus 1. Okay, I'm sorry, I have to do square. It is f in Cartesian coordinate, it is fx square plus fy square plus 1 square. So dfr theta by dr is minus r divided by square root of a square minus r square. If I do square, then it will become r square divided by a square minus r square plus f theta or dfr theta by d theta 0 plus 1 square 1. If I settle it, then it will be a divided by square root of a square minus r square at the end. So a divided by square root of a square minus r square. A is constant, I can take outside. Now what is d area? Area along r theta plane, what is the area? So area is r d theta dr. Please watch previous video. So r d theta dr or r dr d theta, that is dA. Now net integration becomes r divided by square root of a square minus r square dr d theta. Okay, so this integration would be, I am not very good in calculating differentiation and integration, so we will try r divided by square root of a square minus r square. So I believe the integration for this will be minus square root of a square minus r square, minus square root of a square minus r square. This will be integrated, because if I differentiate it back, then minus minus cut down and it will be r by square root of a square minus r square. Just now we saw. So now finally we got the integration, and that integration for the r by Square root of a square minus r square is minus a square root of a square minus r square. That is the integration. Now, the limit. Now, just watch carefully. So, if I cut it at the middle, equatorial, then it is hemisphere. If it is hemisphere, if it is hemisphere, and then we cut from the top also, little bit. Okay. Now, it is a hemisphere slice. Hemisphere slice, we are trying to calculate the slant, the surface. At the center, it is flat. So slant surface, if I take the radius, then it will not be from 0 to A. It will be where the slant starts from there to A. Please watch previous video for better explanation. Okay. So we have to take, now if this is a curved surface, if it is a hemisphere curved surface, I have to calculate only for the curved surface. Top it is flat. Then where from the curved starts from there till the r theta plane. So at that point, the point is from there to A. So that point, if I see that point, that is r. There are two plane here. If I cut it at equatorial, that is r theta plane. At height h, I cut it again, there is another circle. Here there is another circle. Top circle radius is r, whereas base circle radius is a. So where this r comes down from there to a. So that r is nothing but a square minus h square square. So I have to take the limit from square root of a square minus h square to a. Now I have minus square root of a square minus h square. If I take a, it is 0. Square root of a square minus r square minus square root of a square minus r square is the integration. If I take upper limit a, it is 0. If I take lower limit, then this minus will go. Now, square root of a square minus h square, a square minus r square. R square is nothing but a square minus h square. A gone, only h square. So, square root is h. So, now we have a, I had kept outside, a into h. A into h is the integration. A into h. Now, I have d theta left for the integration. D theta, if I integrate, then it will go from 0 to 2 pi. Then it will become 2 pi a h. Same thing, right? We got earlier also. 2 pi ah. Now, if I substitute ah height with a full hemisphere, then it will become 2 pi a square. 2 pi a square. 2 pi a square is the surface area of a hemisphere. But if I go with the height h and try to get the surface area of the hemisphere, not the top, not the bottom, then it is 2 pi ah. Can you see that we found through cross product of the what we did? So we went with like whatever f r theta, f function over r theta, that was square root of a square minus r square. Then we differentiate, we did partial derivative along r, dfr theta by dr. Then we did partial derivative along theta, dfr theta by d theta, because these are the two orthogonal components in r theta plane. Now, if these are two orthogonal components, don't think that should be x-axis and y-axis. Whatever is the orthogonal component is r and theta. If orthogonal components are r and theta, then it will be like this one. So, two orthogonal components r and theta, then we have to do partial derivative along these two. So, if I do partial derivative along these two, then it will be dfr theta by dr and dfr theta by d theta. And then if I see the vector, so if I take any position vector of the sphere, then it will be r, it will be kind of that position vector. If I take any position vector, then it will be r, there it was I axis. Here I can say r axis, r plus r theta axis plus the FR theta kx, the vertical. Okay, so this is how it is. Now dfr theta by dr, okay, dfr theta by dr, then it will become r axis next gone, and then dfr theta by dr kx, and then dfr theta by d theta, then j plus dfr theta by d theta k. But what is dfr theta? Dfr theta we calculated that if this is a hemisphere, if I cut it at the center and this is xy plane and hemisphere is kept on the xy plane, then okay, so I think it should be all right. Please watch the previous video. It will take time if I try to cut it. Okay. Okay. It is really red. So this is r theta plane and this is hemisphere on top of it. Now if it is hemisphere on top of it, then hemisphere radius, the hemisphere radius is r. Oh sorry, the hemisphere radius, this hemisphere radius is nothing but a, that is radius of the sphere. So when it is touching r theta plane, at that point radius is a. Now if I cut little up at height, the height is a again. The radius here is a, then height is again a. Height is again a. If I cut here at height h, okay, if I cut it here at height h, okay, so if I cut it here at height h, then that cross section will be again a circle. This cross section is a circle. If at height h, that is lower to a, if I cut it, then again there will be a cross section circle whose radius is r and height is h. Then diagonal, if there is a circle, then there is a center r, height h, and there is a diagonal. Diagonal is again a. Then what is height? That is fr theta. Then height is nothing but a square minus r square. So fr theta is a square minus r square square. Now we saw that dp by dr is r vector plus d fr theta by dr k vector. dp by d theta is theta vector plus 0, because dfr theta by d theta, where fr theta is the square root of a square minus r square, there is no theta, so it is 0. So it is only theta. So r, k and theta. Okay. So if I do cross product, then r cross product with theta will give me just k, whereas k cross product with theta will give me minus r. So we have now minus dfr theta by dr r vector plus k vector. This is the dp by dr cross product with dp by d theta. Okay. Now if I calculate the magnitude of it, then it will be dfr theta by dr whole square, dfr theta by dr whole square plus dfr theta by dr whole square, dfr theta by dr whole square plus 1 square root. So that is nothing but we calculated. So dfr theta by dr is nothing but minus r by square root of a square minus r square plus, okay, so This whole square is r square divided by a square minus r square plus 1. It will settle down in a by square root of a square minus r square. A square minus r square. Now, a square, I mean a by square root, 4 root. So, a by square root of a square minus r square. A I can keep out. Then I have to integrate now the 1 by square root of a square minus r square against the r theta plane. R theta plane, d of r theta plane is a circle of radius a, whatever it is. That the dA, d of the area, dA is nothing but r d theta dr, r d theta dr. If that is true, then it becomes r divided by square root of a square minus r square dr d theta. A is outside. If I integrate, it becomes square root of minus square root of a square minus r square. Limit is now. So if this is hemisphere, then if I cut it from here, okay, if it is hemisphere, if I cut it here at height h, if I make a cut, then the top circle has a radius r that is smaller than this r theta plane a. If r theta plane is a, then cross section is r. The r, from r the sphere curve starts. So that r, from r till a, that is the limit. R, okay, the top cross section radius is r, and r theta cross section is a. Then from r to a, r to a, that I have to take, so that the slant region volume I can get, not the central cylindrical region I'll get. That I will not get. Okay, so that curved region volume I'll get. If that is the case, then I have integration as minus square root of a square minus r square. So I have to set limit from r to a. R is nothing but the top cross sectional radius. That is nothing but a square minus h square square, because I have to find in h. So now I have limit from square root of a square minus h square, and top is a. If I put a, then it becomes 0. Then lower limit I put, then minus will go. So square root of a square minus r square. Now r is square root of a square minus h square. So it will become h square square root h. A outside, a h. Now there is a d theta integration I have to do, that is 0 to 2 pi. So net volume of the hemisphere, where there is a surface, not the top portion, that is cylinder. So that portion is curved is 2 pi a h. If the h height is full, there is no cut, that is a. So 2 pi a square. That is the surface area of a hemisphere. But if it is this is the case, then what is, if I make a cut at height h, if I make a cut at height h, if I make a cut, then that height, the circle, what is the surface area of that circle? Okay, so the radius there is r. So the area is pi r square. R is nothing but square root of a square minus h square. So pi r, and then braces a square minus h square. Okay, so pi, okay, so braces pi a square minus h square. Pi a square minus h square. If that is the case, then the top area is pi square root of a square minus h square. Now bottom area is pi r square, so pi a square. So net the steel surface area that will be required here is pi a square, that is bottom one. Curved one is 2 pi a h, plus the flat top is pi, and in braces a square minus h square. If h is a, if h is a, then what is the surface area? If h is a, Then first is pi a square, second is pi a square, second is 2 pi ah, it becomes 2 pi a square. That is the area of hemisphere. Next is a square minus h square, then that is gone, 0. So net required is plane pi a square and then full curved surface area, that is pi 2 pi a square. What if h is 0? What if h is 0? That is the case, then bottom is pi a square. So pi a square will remain, and then curved a region is 2 pi a h. So h is 0, that is gone. Now then pi pi braces a square minus h square. Okay, so a square minus h square, h is 0, then again it is pi a square. So top portion coincide with the bottom portion. So 2 pi a square is coming. Okay, so we have finished now the various coordinate system, because we have done all permutation combination what we could have done. So four coordinate system we talked about, uh, Cartesian coordinate system, polar coordinate system, where the Cartesian coordinate system, the independent variables are x, y, and z. Polar coordinate system, independent variables are r and theta, where the dA area is arc into radius. So arc is r d theta and radius is dr, or dr d, or r theta is the arc and r is the radius. Okay, and then we have kind of cylindrical coordinate system, that is polar coordinate system, which has a height, that is cylindrical. So r, theta, and z, there are three components that comes into the picture. So dv, small volume dv, there is nothing but r d theta, dr, dz. Then we came to a spherical coordinate system that is heavily used in cosine distances that we do in machine learning. Please refer to our latest disclosure. So go to Google and type unsupervised learning, unsupervised learning, clustering, and k-means. K-means. K-mean is an algorithm. K-means. Okay, and type code project, CODEPROJECT, codeproject.com, whatever, code project. Then you can see our art, and there you can see that we have used a spherical coordinate system as far as cosine distance is concerned. We have used calculus to prove the partial derivative and how re there are two phases. One is reassignment phase and recomputation phase. So in recomputation phase, we try to find the mean. So reassignment phase, anyway, we go with the cosine distance blindly. But in recomputation phase, not reassignment, recomputation phase, where we calculate the average, we recalculate the position of mean in its cluster. There, what is the mathematics we have to use? So we went with the derivative, partial derivative in a spherical coordinate system. This is exemplary, that you have to must watch. And then all examples we have come up with, all are fresh new examples that we have seen. Okay, we have written it from scratch also, the algorithm. So that can be seen. Just type unsupervised learning, clustering, and k-means code project. So you will come to our kind of disclosure. So there you can see cosine distance as a spherical coordinate system. So in a spherical coordinate system, if I have dv, small dv, that is nothing but if I have now in a sphere, radius is not limited to xy plane. Radius, same radius is everywhere. So there is a angle from vertical, that is phi. So if I take a dv, then it has three sides. One is horizontal arc, one is vertical arc, and another is radius. So vertical arc, if there is a vertical axis and there is a phi angle, then a d phi is the vertical arc. A sine phi is the along the r theta plane. So A sine phi d theta is the another r. One r A sine phi d A sine phi d A sine phi d phi or r sine phi d r sine phi d theta. One is r d phi and one is dr. So r sine phi d theta, r d phi and dr. These are the three components for the dv in a spherical coordinate system. Not only that, we showed two ways to calculate the integration. One is through dv, everywhere get dv and do the triple integration, or you go with algebraic equation and do dual integration only. So algebraic equation you calculate and integrate along the r theta plane. That's it. Triple integration is not required. That is the core calculus. So we have done all permutation combination. Not only volume we calculated surface area, and then we see interoperability along the coordinate system. So interoperability along the coordinate system, if we see, then it is nothing but we start with the Cartesian coordinate system, and then we end up in the some portion we can try with the polar, cylindrical, or the spherical. So this is amazing, right? Hybrid model also we can, because generally people will start from the Cartesian coordinate system, but when it end up in final integration, people may start sweating. I mean, it is difficult. I also start sweating, so it is difficult sometimes. In that fashion, it is clever step to convert the part of this to the kind of to polar coordinate system. So part by part we can change it. If we do in that fashion, then life is easy, where full integration of the Cartesian coordinate portion by portion it is different coordinate system. That is the LY or hybrid model. So that also we see with every possible combination, permutation and combination, generally we say we calculated every possible thing: surface area, volume, through dual integration, through interoperability, from all way. Okay, so it's like if we are done with the various coordinate system. Okay, please watch all the videos and then be ready for powerful machine learning, where we have art of calculus, we have art of algebra, we have art of vector, and we have art of coordinate system. Orthogonal components, we have made series of orthogonal components, orthogonal component calculus that can be worked. Everything we have done. So we'll proceed with kind of new things like flux, very important, flux, curl, and those kind of things that we will proceed.